Welcome back, physicists. Today, I think, and I'm pretty confident, we're going to finish chapter 14. Pretty sure it's going to happen today. So, we will be concise with this. 14.3, our entire focus, half of it was a lab, which we're just going to summarize some basic ideas now. The other half is another little demonstration that we'll see up there. But all I care about in 14.3 is the behavior of gases. Now, as we looked on the quiz just now, gases can compress, fluids can't. That's the reason that we use gases can compress, liquids can't, which is why we use liquid when we're doing hydraulic stuff. So at this point in time, really, we just need to summarize one relationship, and then we'll see that there's another one just kind of lurking around the corner. So before writing anything at all, the first kind of little piece that I want to look at is really what we're focusing on here. I want to know, how do pressure and temperature relate? Now, when we talk about they relate, we're looking at how do they interact when we're dealing with gases. That's the whole focus right now, because clearly temperature is going to change something, pressure is going to change, and there's one more little piece that's kind of hiding in here. But as a quick little summary, we looked at a lab the other day, the last couple days. Do you remember the law that we worked out in that lab? It's not Bernoulli. Boyle. We looked up Boyle's Law. And we worked out, and I'm going to make this all caps, Boyle's Law. Now, the entire lab was focused around Boyle's Law. Now, very specifically, we're going to define this here in a second, and it's one that you should wait if you can. Okay. Boyle's Law, we're going to define this, but the one way that I would write this down first is when we're dealing with Boyle, I want us to make sure that we're aware that we're dealing with volume. And if you think back to the simulation, it was volume that we were changing the size of the box, right? And we're recording the changes in what as we change the volume? Yeah, volume and pressure, absolutely. Now, there are a few ways that we can do this. Boyle's Law, the conclusion that I hope that I'll be able to see on our simulations, everybody hands in, is that if we happen to get a container and we're able to keep it at a constant temperature. So we have a gas at constant temperature. A gas, and I'm going to say a contained gas to make sure it's not just kind of out there in space. A contained gas at constant temperature. Okay. If you have a contained gas at constant temperature, and I'm just going to put a semicolon because that's just like the piece that we need to assume. What's constant when we're dealing with Boyle? Temperature. We don't change the temperature of the gas. It's contained somewhere at some given temperature. The contained gas at a constant temperature has the following relationship. The volume of the gas, and I'm going to say of gas, turns out inversely proportional, or it varies inversely. I'm going to say is inversely proportional. Inversely proportional to the what? And I'm going to pause there because I have a feeling that there's some math language that people don't love. It's the volume is the next word that I'm going to write, absolutely. What does it mean to be inversely proportional?
It's like
opposite, kind of. As one goes up, if it's opposite, what does the other one do?
down.
Goes down. Now we'll summarize that, we'll make it easy to deal with. So the volume of a gas is inversely proportional to the, I lied, Kian, it's not volume. Pressure.
Yeah, because it would be the same.
Yep. Okay. Now what this means for us. Here's the statement of Boyle's Law. The volume of a gas, it varies inversely or is inversely proportional to the pressure. Means that we can think of this as a nice, easy way. Now, I'm going to use IE, which is like in other words, is what this is. If pressure increases, do you want me to write increases or goes up? Increases. If pressure increases, then, assuming that we're at constant temperature, what does the volume do? Good. It must decrease. Now, this is all the wordy version of what that lab was, or that simulation was supposed to be demonstrating. And I think you guys probably saw that happen. If you make the volume larger, the pressure goes down. If you make the volume smaller, the pressure goes up. They're opposite directions. So mathematically, there's a nice way to write this. Before we write down the mathy version of it, is there any part of this that somebody looks at and goes, I don't really quite get what this is saying? Can I move stuff around and change directions? What if volume increases? What changes? If volume increases, pressure must decrease, right? And I can move this around however I see fit. So I would like to, because you guys have written this multiple times, I would like to write this one time in the nicest fashion that I can. And if we need to expand on it, we will. So here's kind of my big idea with Boyle's Law. It tells me that if I write PI VI, that is exactly equal to what? So I like the OYO out of curiosity. So initial pressure times initial volume is equal to what? The final pressure times the final volume. Now, every single time, this is going to work out. I get this goofed up in my head because we're going to learn another law that deals with changing different things today. But if you take the pressure times the volume initially, and you know it's going to be equal to the pressure times the volume in the end. Now, on your simulation, those of you that handed in last week, it didn't work out quite perfectly. Those of you that asked anything about it, I want to highlight. On our simulation, do you remember how many particles we had in that chamber? A couple hundred, right? Like 300 maximum. In reality, if you're dealing with any chamber, how many particles are there going to be? Like trillions of them. Like, we see little tiny changes, individual collisions happening. One of the fundamental pieces of our kinetic theory, which says everything's wiggling and bumping into stuff, one of the fundamental pieces is that each individual particle carries such small energy that's essentially negligible. You can ignore it, which means on a real pressure gauge, you're not going to see it wobble, ever. Okay, now as we're dealing with this, what is PI? Okay, so we're just, if you need this, I would like you to write it. PI is initial what? Pressure. And I'm just going to write two of them and we can, I assume, extrapolate or reason out what happens. What is VF? Final volume. Now, instead of me writing it the other way, I don't think I need to write the other two. If I know that PI is initial pressure and VF is final volume, what do you think PF might be? Final pressure. What about VI? Initial volume. Do I need to write the other two if we know this notation? Sub I, or a little subscript as an I, is initial, right? Okay. Now, this is Boyle's Law. This is the whole point of that simulation we did the other day, to make you guys see that this does indeed work this way. Now, beyond that, do you want to do a problem with this one first, or do you want the other law that we're going to get? Problem first? Okay. Now, I go back and forth because in my mind, I don't know if it's more valuable for you to just be able to apply this immediately or to be able to identify, what matters about the problem so you can pick it out. Because on the test, am I going to tell you use Boyle's Law or use this other law? I'm just probably going to tell you to solve it, right? So you have to be able to distinguish between them. Boyle's Law, just write first and foremost on this very first line. I wrote something to tell you when Boyle's Law applies. It's when you're dealing with what? Volume and pressure. Good. That's, if you have volume and pressure given, pretty good chance it's going to be Boyle. Okay. Beyond that, let's knock out a problem here. I think neither of these are super challenging. Let's check it out. Okay, we're told that we have example. We'll do Boyle's example. We'll do one together, and then I'll have you guys do one with your neighbors. So we're going to take some helium. What is helium? Yeah, it's one of the things you put in balloons. I wouldn't say common necessarily. It's actually pretty rare. When it's an element, which means it's like the most simple version of something, just like oxygen's an element and iron and all those things. Anybody know the symbol for helium? He. He. I'm sorry? This one works for English. This one's nice. Okay, some helium, which we will be dealing with this in the coming chapters, is He. Lando, what's up? If you hustle. Oh yeah, absolutely. Because it's less dense gas, it makes your voice go up. Trace. Oh, yeah. I'm sorry. Yeah, you can go too. You're good. Don't cause a ruckus. Okay. Anyway, helium makes your voice go very high. Like.
That's why his sign is heat. So you laugh about it.
Good thought. Maybe. I have no idea. I like it. That's what I'm going to tell my chemistry kids. All right. So here we go. We're told that we have some helium, which is a gas that fills 11 liters of volume. So it's just like if you have a balloon, like if you think of a liter of water, that's just some amount of water, right? Is there also, I'm trying to write 11. I just don't know. I'm trying to change the way I write my ones. But we'll do this. 11.0 liters. Yeah, there's some weird stuff that happens with L's and all that. 11.0 liters. Everybody okay with what that says? All right. So we have a balloon that fills 11 liters, and in these 11 liters, we have the following pressure. It's 98.0 kilopascals. Notice, kPa with a capital P. All right. Here's what I want to know. If, just hypothetically, if the pressure drops, and there's various reasons why the pressure would drop, but if the pressure drops to, let's say, I don't know, 98 kilopascals. Whoa, that's not right. 862, there we go. And we'll make it 86.2 because I can't read. Kilopascals. I want us to find the what do you expect I'm going to ask about. The new volume. Okay. So we have a balloon that's 11 liters at 98 kilopascals of pressure. We're going to drop the pressure. Now I need to think about what's going to happen with the volume. Now, right off the bat, if pressure decreases, according to Boyles' law, what should happen with volume? Volume should increase. So right off the bat, before I do anything, should my answer be larger or smaller than 11? Larger. It ought to be larger. If I get something smaller, it's a good sign that I've done something incorrect. And it happens. So let's just make sure we can knock this out. Do you want to do the knowns and stuff together? Or do you want a second to see if you can identify everything before we do it as a class? Okay, let's talk out the first one together, and then the second one, we'll completely switch it out. So here we go. As I'm looking at the information that I know about this problem. First things first. I don't know anything because I'm really struggling. But let's see. Freddie, we made eye contact. What are one of the things that you know here?
11.0.
So when you talk about a liter, it's an amount of space that you're occupying in the universe. That is a way to write down which quantity. Space you occupy, sorry. Starts with a V and ends with volume. Volume, there it is. So check it out. Now here's the deal. Is this 11 my initial volume or my final volume? That is my initial. So VI equals 11 liters. 11.0 liters. Liters is just a capital L. And I draw my capital L's as fancy cursive L's for some reason. Okay, so I know 11 liters. I'm just going to put a little check mark or a strike through to say I've already written it down. What else do you know? Lando, you weren't here. That's not fair. King, give me something else you know.
9 kPa.
What is KPA? So that is a good answer. What is that representing, though? Is that pressure? Is that volume? Is that velocity? Is that acceleration?
Pressure, I think.
It better be pressure. We haven't talked about velocity and acceleration at all. I just wanted to make sure. There's only one other word that if I just said, is that pressure? That's a poor question. All right. So is that the initial pressure or the final pressure?
No, initial.
You're changing your answer based on my facial expressions? Yes. Disregard my facial expressions. I got you. Okay. Pressure initially is 98 kilopascals. 98.0 kilopascals. Is that a lot or a little?
It's a lot.
It's actually a little. Do you remember what ours, like pressure in here, roughly is?
10 to power.
Probably about 101 kilopascals is what I would expect. Around that number. and we'll see that show up. I'll tell you, I don't trust this entirely, but according to my little sensor thing back here, it's actually 100.8 kilopascals in here right now. So 100.8 instead of 101, or yeah. So we're pretty close. That's a little bit lower than regular air pressure, which makes me think this is the sort of pressure you'd get at a high elevation. So maybe you're at a research lab high up in the mountain somewhere. Okay, anything else that I know? I know initial pressure, I know initial volume. Uno más. What do you got, Matilda? I know the final pressure. The pressure at the end of this whole ordeal is supposed to be 86.2 kilopascals. Okay. As long as you can identify that pascals is pressure, which in my mind I always just use the P values, right? Pascal and pressure. What am I trying to find? I'm trying to find the new volume. Give me a different way instead of new volume. VF. Okay. Now, here's the only thing that we need to worry about. I know that we're dealing with volume and pressure. Whose law uses volume and pressure? Boyle. What's the relationship between volume and pressure of a gas that's held at constant temperature? So that's a good way to give me the wordy version. What about the actual formula, the equation that we can use? P-I-V-I-O. Don't throw an O in there. I'm sorry. That's a terrible thing for me to do. I should not have even put that thought in your head. Pi times Vi equals PF times what? VF. Now, as far as this notation goes, if you like math and you enjoy algebra, or maybe not necessarily algebra 1, but if you enjoy any math at all, when I don't put anything between this, when I just say Pi Vi, what does the implicate, like what am I assuming we're doing?
We're multiplying.
So not the i's necessarily. If I just say xy, what happens between xy?
Multiplying.
They're multiplying. If you see two variables immediately next to each other, what's the operation that you're allowed to assume, King? Indeed, I'm going to make you move behind Kennedy because this stuff's super important. Okay, if you see two things next to each other, anytime, two variables, they multiply. So without me saying it or writing it, I could really say this is Pi times Vi, but it's redundant. We don't really truly need it. Now, I'm trying to solve for VF. Two things that are going to make this easy. Go, Joe. First and foremost, V sub F is on which side of this equation right now? On the left or the right of this? Yep, V sub F, what we're trying to solve, is on which side of this equal sign? On the right side. Now, when you guys solve in math, it's most natural to put the thing that you want on the left, right? On the left, do you agree? Okay, so normally that's the way it works, but I'm not going to do that until the very end. Riley, on the right side, I'm after final volume. What is it multiplying by? Good, so VF is my final volume. That's what I want, and I'm multiplying it by the final pressure, right? Now, the good news is that mathematically, there's nothing crazy going on. Lando, to undo a multiply by final pressure, what undoes a multiply? Divide. Let's divide by final pressure. Which side of my equal sign should I divide by final pressure? So I'll do it there first, but I better do both, right? Equations, they're scales. One thing on both sides. So check it out. Yep, exactly. I'm going to divide this side by PF, and I'm going to divide this side by PF. Everybody cool? Yay, nay? Okay, now what happens on this right side with this PF and PF? They gone. So check it out. I now have Pi Vi divided by what? Whoa, whoa, whoa. Go ahead.
Where are your numbers?
I'll put them in here in a second. No, I'll plug them in here in just a second. Trace.
I'm sorry, is that 86.2 or
86.2. Yep.
Okay. Can I wash my glasses?
Yeah, if you wait till the end of this, that'd be ideal. Okay, Pi Vi divided by PF is exactly equal to what's the only thing that's left on the right side? VF. Do I know the value for Pi? What is it? Try again. Just kidding, I'm wrong. I'll try again. Yes, that's correct. Okay, initial pressure is 98 kilopascals. 98. Do I know the initial value for the volume?
Yeah.
What is it?
11.
11 liters. Here's my 11. Do I know the initial value, the final value for pressure?
Yeah,
86.2, okay. At this point, do you want to do this like by hand? Really?
Definitely.
I don't really want to do this by hand because I don't like long dividing if I don't have to.
You said like you do it yourself.
Oh yeah, I'm just gonna make you guys type it into your calculator or your phone. Verify you get the same thing. And I'll work this direction. I need to verify that you guys are able to get this answer. See, you got one already? We'll hold on to it for just a second.
Isn't it 90-something.2 though?
It's 12.
Isn't it 90-something.2?
I got 12.5.
12.5 is one suggestion. Seconded, 12.51. Thirded, fourth, fifth, 12.51. Let's round it since we only ever use 3 decimals. That's 12.5 what?
12.50.
Okay, I'll just put 12.5. I'm just going to round it to 3. Now, here's a bigger question. We found volume. In this problem, how was volume measured? What was the unit on volume? KPA is pressure, because PA is P is Pascal is pressure. That's a dumb little thing I did in my head. Liters, absolutely. Liters. Did it increase? Should it have? Absolutely. My answer, I'm confident with it. We are solid there.
Forget your cube.
Why would I do something cubed? Nope, liter is it's already dealt with. Liters cubed is a bigger dimension thing. No such thing.
Oh boy, how much?
Yep, so get rid of your cube. We don't want it. Yo! How much money you got?
I got $20 in my pocket.
Yes, you can go. What year bill is it? All right, so, okay, another one of Boyle's Law. You can go wash your glasses. Another Boyle's Law, or do you want to get one more different law real quick? That one's seemingly okay. PIVI? PFVF. Yeah, all right. Now, apart from Boyle's Law, there is one more law. Okay, if you need to go to the office, do you have a headache? Okay, please don't throw up there. You can go to the office if you need to. I know it's not in your control, obviously. But all right, Boyle's Law, and this will be recorded for you if you wind up missing stuff, so don't stress. Okay, Boyle's Law is one of them. Now, instead of holding the temperature constant, I'm just going to pop over to the simulation real quick. I'm going to put a couple particles in here, and we'll add more. Instead of putting the temperature constant, could I keep the pressure constant?
Yeah.
Now, I'm going to add some more stuff in here real quick, and I just want to see what happens. If I want to not change the pressure, not directly anyway, what other quantities could I possibly add? I'm going to get a bunch of particles in here. If I want to change the pressure, and it's going to start changing a little tiny bit, right, because the particles are hitting. But if I want to change something else, what could I change? I could change the volume. That's something we've already changed, right? Or the temperature. Now, before, we were changing what? The volume, and that led to changes in the other pieces, right? So I put one red one in there just for fun. So here we go. All we're looking at, what's up? Or he's bullying. She, they, I don't think they are. I don't know the. Yeah. Anywho, here's the whole point of this. As we get with Charles' Law, I'm going to change the temperature. I don't want to change the pressure. If I heat this up, what happens with the particles? How do they move?
Faster.
They move faster. When you heat up a gas, anybody ever bought a balloon at Safeway? And it's all big and puffed up, and you take it to your car, and it's sad.
Yeah.
And then you get back in your car, and you turn the heat on, and you're driving, and then it gets happy again. What's happening? You're not changing the amount of gas in there, are you?
Yeah.
You're definitely not. You're not untying it, and why is the pressure changing?
The temperature.
The temperature is changing, and the volume of the balloon is changing because it's either shrinking or expanding. Now, if I heat this up, if I don't want my pressure to change, what do you think has to give? If I heat it up, does the volume get bigger or smaller?
Smaller.
You think so?
Yes. No.
Let's try. I don't know. We'll heat it up. Oh my goodness. because my pressure can't change. If I add energy, they move faster, they hit harder. But if I don't want my pressure to increase, I also have to make my volume bigger. Now, if I cool it down, what will happen? It should shrink theoretically.
You have to put it back.
Do I have to put it back?
No,
Put what back?
pressure thing. It changes.
Oh, I didn't even see it change. That's no fun. Okay, if I make it colder, it cools down, it gets closer together. I can change the size of this. Now, this was discovered by a guy by the name of Jacques Charles. He's a French math, Jacques, or Jacques.
Sounds like, what's that guy from Beauty and the Beast? He's like Dr. Strong, he's got the red shirt.
Probably Jacques.
Probably
Good call. I would have guessed Jacques for like 90% of it. Anyway, Jacques Charles was a French physicist, chemist. Here we go. We get Charles' Law. Okay. Now, just real quickly, what does Boyle's Law deal with? Volume and what? Volume and pressure. Volume and pressure is Boyle. Okay, for Charles, we're going to be dealing with temperature and volume. Temperature and volume. Okay, those are kind of big takeaways. You need to be able to identify in a given situation whether it's a Boyle's Law problem or it's a Charles' Law problem for our stuff that's coming up. So here we go. For Charles' Law, we're going to work with a similar assumption. With Boyle's stuff, we said let's keep this at a constant what? What didn't we change with Boyle? We didn't change the temperature. For Charles' Law, we want to keep our gas at a constant pressure. So we're going to say with an enclosed gas, held at constant pressure. Means we can't add particles, we can't remove particles. All we need to do is just change how excited these particles are inside. So if you give me an enclosed gas that's held at constant pressure, if and I'm going to come back over here to this simulation here in a second, if you increase the temperature, what happens to the volume if you don't want to change the pressure? So let's check because I think I hear both of them. Here's my constant pressure. I'm not going to let it change. I increase temp. What happens to volume? It gets bigger, which means increases or decreases? If I increase temp, I increase pressure. Sorry, I increase volume. What if I increase volume? What do you think is going to happen with? So I want to keep the pressure constant, though. If I increase the volume, the temperature must also increase to keep that same pressure. Now, that is a nicer relationship. The inverse one that we get before, one up, one down, can be wonky. This is so much nicer. So here we go. The pressure. Now I'm going to say not the pressure, rather. The temperature. And this is a weird one, but it's super important. When we measure temperature, most commonly we use which unit in here? Celsius. Degrees Celsius normally is what we use in here. For this law, the temperature must and will always be in Kelvin. And if you don't remember how to get there, it's easy. I'll remind us. The temperature in Kelvin, we're going to say it varies directly as the volume. We'll say the volume of the container. The temperature, which we will measure in Kelvin for this circumstance, varies directly as the volume of the container. Which means temperature goes up, volume goes up. Temperature goes down, volume
Goes up.
down. They both go the same. Now, for this, I'll just write the same thing, another IE. Temp up. And I'm going to say temp increase, volume increase. Do I need to write temp decrease, volume decrease?
Yeah.
No. Now in my notes I actually have if and only if, so it goes both directions. If you're not in geometry yet, you have no idea what I'm talking about with that. Okay. Now, other part here. Who is confident in their ability to move between Celsius and Kelvin? Can you move between Celsius, degrees Celsius, and Kelvin?
Maybe so.
It's way easier than that. So we have it written down somewhere in our notes. I don't need you to find it again. It's so easy. Recall. Do you want to go? Something that I say, my phone thinks I'm talking to Bixby, and I haven't decided what it is yet, but it keeps talking to me just randomly. Was that my phone that just talked or somebody else's?
Siri does the exact same thing.
My screen doesn't work.
Okay. Here we go. Recall. Really important. We'll come back together. All right, here we go. To go from degrees Celsius to Kelvin. Notice, I don't say degrees Kelvin because we don't use degrees Kelvin. It's just Kelvin. To go from Celsius to Kelvin, all we need to do, super duper easy, we take some degree of Celsius, which I'm going to use X. X degrees Celsius, and all we need to do is subtract 273. And we wind up in Kelvin. You take some temperature in Celsius and you subtract 273 and you now get Kelvin.
So if you have 73 in Celsius,
Negative 200 Kelvin. 73 Celsius minus 273 is negative 200 Kelvin. You just subtract. So, to go from Kelvin to degrees Celsius, which is a valid question, just go the opposite direction. Instead of subtracting 273, what do you think you do? Yeah, you just add. So we're going to say X Kelvin, that's some number, plus 273. So 0 Celsius is how many degrees Kelvin? 0 Celsius. Negative 273. What about 0 Kelvin? How many degrees Celsius is 0 Kelvin? Try again.
negative 73.
Try again. 0 Kelvin plus 273 is
273.
273 degrees Celsius. Okay. Yes, sir. Where? Because notice one's going from Celsius to Kelvin, so we subtract, right? To go, what's the opposite of subtracting? Want to go the other direction? Yep, that's all that's happened. Okay. So here we go. That recall we will use immediately. And let's knock out an example. How hard of an example do we want? None of them are hard. All right. So here we go. On example, we're just going to go ahead and say that this is Charles' example. Because we're doing Charles' Law. So our first example, I think, is Boyles' Law. We're going to be dealing with Charles here. Okay, here we go. We are told the following information. We have a balloon that is a 2-liter balloon. A 2-liter balloon. At room temperature, which real quick before I write it, what's room temperature? 70 Fahrenheit, roughly. But we don't ever use Fahrenheit. Anybody remember? 20. Okay, a 2-liter balloon held at 20 degrees Celsius. Lost my spot. We put it in the fridge. What's going to happen to this balloon, you think?
It's going to explode.
Why? It's going to shrink. 3 degrees Celsius fridge. Because, Landon, check it out. Are we going to be able, we can't add particles in or out of the balloon, right? It's tied up. If you decrease the temperature, what happens to the volume?
Oh, it's going to triple up.
It's going to decrease, right? Okay. 2-liter balloon at 20 Celsius is put into a 3 degrees Celsius fridge. All I want us to do is after it's been cooled down completely, I want to find the new volume. Find the volume of the shrunken balloon. And you can just say smaller if you'd rather. That's our whole goal. We're looking for the new volume. So as with like every problem we've ever done in here, right now to begin this, what should we do? I'm going to write down the knowns immediately. So we'll switch color here. Did I write something funny? No? Okay. All right. What do I know? I don't know any of it. Uh-oh. How do you write that down?
What's the VI?
Yeah,
VI, my initial volume?
Oh,
Maybe. We'll see. Let's get our knowns first. The initial volume is what? 2 liters. 2.0 liters. Okay. Now, before we do this, I do want to address your question, Angel, because it's nice to think about it as you're writing your knowns, but it really shouldn't matter. You'll decide once you have the equation down. We have volume and temperature. Is it still boil? It's definitely not. But what else do I know? I know my initial volume. Mark, can you tell me anything else that you know based on this? Okay. Perfect. So we're going to use TI, and we should probably give ourselves a mathy version of Charles' Law, but we'll get it. Okay, the initial temperature, capital T sub I, is what? The initial is 3? 20 degrees Celsius. Now, here's the weird little part that we need to think out. Up above, we wrote just a minute ago, and we'll write out the actual equation, because we didn't do that for Charles' Law. I should have. But what do we want the temperature in? Kelvin. How do you... We don't have Kelvin here.
Minus 273.
Are you sure? Celsius to Kelvin. Yeah, let's subtract 273. I'm cool with that. So what do we get for the initial temperature here?
Oh, and then you get
So let me see. Celsius to Kelvin.
you get 253. Negative 253.
So time out. I'm all goofy here. I think give me like 30 seconds. I gotta look at this real quick. Yep, I'm goofy. We're gonna make one little change. I just have this backward here in my head. Because 0 Kelvin is absolute 0. The very coldest you can possibly get. We're gonna make this first one a plus. Celsius, 2 Kelvin. I'm sorry, we're gonna make that a plus right there.
So I was a little confused.
Is that... Explain to me why you were confused.
Because when I did like mess with the thing, it was 27 for the Celsius and like 300 something.
What do you mean you messed with the thing? What thing were you messing with?
Temperature.
Oh, okay. Yep. No, you're absolutely right. Which means if I change that one to a plus because I got stuff goofed up, what does this one change to? A minus. Okay, terribly sorry about that, guys. Gosh, we're in a weird situation here right now. I want you to write down as the rest of the knowns and what you're asked to find. We may have to push and have like a take-home assessment over the break. You say no. Why would you say no to that? Over your 4-day weekend, you might have a take-home test. That's what might be shaking out right now.
Take home test?
Yeah, that's a good thing.
Wouldn't that, I think we'd be good here. But right now, because we'll make sure we'll jump in, we'll finish this problem tomorrow. I want you to continue, get me the rest of the knowns, you're fined, and then we'll work out the equation stuff tomorrow, okay? Okay, before you put stuff away, you got 60 seconds right now. You should be able to get down the rest of this information. False. Sorry? Well, we don't have it yet. I mean, we do here in words, but I was trying to rush it, and that's what threw me off.